Hello students, in my last lecture on real gases, I had discussed various experiments which are needed to understand the behavior of real gases. I had also derived the very famous van der Waals equation of state to understand more about real gases. And we had seen that there are two constants that appear in the van der Waals equation of state. These constants are A and B. Now let me take this lecture even further and explain you the significance of the constants A and B. I will first explain the significance of the constant A, which appears in the term P plus A by V square. This constant A originates from the intermolecular attraction, and Pa is equal to An square by V square. Thus, A is a measure of internal pressure of the gas, and so the attractive force that exists between the molecules. Higher the value of A, greater would be the intermolecular attraction, and more easily the gas could be liquefied. Let me now show you briefly what is the expected value of A for various gases. For carbon dioxide, A is 3.95 atmosphere liter square mole minus 2. For hydrogen, it is 0.22 atmosphere liter 2 mole minus 2. Because the value of A for hydrogen is very less, we can infer that it is difficult to liquefy hydrogen. Now, what is the significance of the constant B? B measures the molecular size. B can be utilized to calculate the molecular diameter, which is given by constant sigma. Greater the value of B, larger would be the size of the gas molecules. Thus, we can say that B of CO2 is 0.04 liter mole minus 1, whereas B of hydrogen is 0.02 liter mole minus 1, half of what is the B of CO2. This table is showing values of A and B for various gases. I have highlighted argon and helium here. For argon, you can see that A is 1.35 and B is 0.0322. For helium, it is 0.034 and the value of B is 0.0237. Now let us calculate the Boyle's temperature for a van der Waals equation. To calculate the Boyle's temperature, we know the general condition is Tb is equal to dPv by dP at constant temperature. That is, we are taking the differential of Pv with respect to P and at constant temperature. The van der Waals equation for 1 mole of gas is P plus A by V square into V minus B equal to RT. Just simplifying this equation of state, we get P is equal to RT over V minus B minus A by V square. Multiplying left hand side and right hand side by V, we get PV is equal to RTV over V minus B minus A by V. To calculate TB, we have to differentiate PV with respect to pressure at constant temperature. So, if I differentiate PV with respect to P, I get RT over V minus B minus RTV over V minus B whole square plus A by V square. Simplifying the right hand side, we get RTV minus B minus RTV divided by V minus B whole square plus A by V square. Simplifying the right hand side further, we get minus RTB over V minus B whole square plus A by V square. When T is equal to Tb, we get d of Pv by dP at constant T is equal to 0 and dV by dP is not equal to 0. Thus, we now have for T equal to Tb, RTB B over V minus B whole square is equal to A by V square. Here Tb stands for the Boyle's temperature, and remember The concept of Boyle's temperature originated after Amagat's experiment. Tb is now equal to A by Rb, V minus B over V whole square. Since P approaches 0, V is large, thus V minus B by V. We can neglect B in comparison to V and we get V minus P over V equal to 1. Hence Tb is now A by Rb. A very important result, because as you can see, A is van der Waals constant, R is the gas constant and B again is the van der Waals constant. So we have expressed Boyle's temperature in terms of three constants A, R and B. Now what are the merits and the limitation of van der Waals equation of state? This is very important to understand. What is the importance of van der Waals equation of state? Van der Waals was able to predict the behavior of gases better than the ideal gas equation, especially at low temperatures and high pressures. The van der Waals equation of state is applicable not only to real gases but also for fluids. So this is very important. The van der Waals equation of state, we were able to calculate the critical conditions of liquefaction and derive an expression of the principle of corresponding states, which I will be doing it in a few moments. Then these are the important aspects of the van der Waals equation of state. Then what is the limitation of van der Waals equation of state? Van der Waals equation of state has certain limitations. The first being varying values of the constants A and B with temperature contrary to the assumption made by van der Waals. A and B are not constants, they vary with temperature. So this is one major limitation of van der Waals equation of state. We will calculate Vc equal to 3b in a few moments for all gases independent of their nature. But experiments showed that Vc varies from 1.4b for argon to 2.8b for hydrogen. It is not a constant, it is not equal to 3b. It varies from 1.4b to 2.8b. So this is again something which is against the prediction of van der Waals equation of state. So this is another limitation of the van der Waals equation of state. Van der Waals equation of state showed that the critical coefficient, which is defined by RTC over PCVC, here Tc is the critical temperature, R is the gas constant, Pc is the critical pressure, Vc is the critical volume, should be equal to 8 by 3 irrespective of the gas considered. But it is different for different gases with values which vary from 3.28 for hydrogen and 3.48 for CO2. So it is not a constant. Van der Waals equation of state showed that the Boyle's temperature for a van der Waals gas is 3.375 into Tc. But it was observed that the Boyle's temperature lies between 2.5 Tc and 3.7 Tc. This is again in variance with the theoretical value of Tb as calculated from the van der Waals equation of state. So this is again an important limitation of the van der Waals equation of state. Limitation means the theoretical results are not matching the observed results. Another limitation of the van der Waals equation is in the form of the carbon dioxide curve, the isotherms obtained in the carbon dioxide curves. All the isotherms at the critical point and above it, the point at which CO2 exists in both liquid and gaseous states, are similar in the case of van der Waals graphs and the tested graphs from Andrews isotherms. However, below the critical point, the isotherms from Andrews sit higher than those representing the van der Waals equation. Besides, the van der Waals equation isotherm has one minima and maxima which isn't described in Andrews experiment. So this is another variance of the theoretical curve with the experimental curves. Besides, the van der Waals equation has one minima and maxima which isn't described in Andrew's experiment. Next, let us calculate what is meant by the compressibility factor. What is its physical significance in real gases? The compressibility factor is a measure of the deviation of the real gases from ideal gas behavior. It is defined as the ratio of the molar volume of an ideal gas at the same temperature and pressure. It is denoted by Z. This graph is showing a plot of Z versus pressure of a few gases at 0 degrees Celsius. So you can see for an ideal gas we are getting a horizontal line which is parallel to the x-axis. For hydrogen we are getting a value of Z which is greater than 1. For CO2 we are getting a curve in which Z is less than 1. Whenever Z is greater than 1, it means the gas is less compressible. Wherever Z is less than 1, it means the gas is more compressible. And remember, ideal gas cannot be compressed. For CO2, the van der Waals constant A is very high. Thus, A by RT is much greater than B in the equation, and B minus A by RT is negative. The slope of Z versus P curve is negative for CO2. That is, the value of Z decreases with the increase of pressure as found in the curve of carbon dioxide. The case is entirely different in the case of hydrogen. For hydrogen, the van der Waals constant A is very high, is very small. So A by RT is less than B. And the slope of Z versus P curves for hydrogen becomes positive. Thus, the value of Z increases with pressure. When the temperature is less than the Boyle's temperature, that is, T is less than A by RB, or simplifying, B is less than A by RT, we get B minus A by RT as a negative quantity. So this curve is again showing the same thing, but with a difference. In the earlier curve, we had shown 3 different gases. Here we are showing the variation of the same gas at different temperatures in comparison to the Boyle's temperature. So as you can see, for temperatures less than TB, the compressibility factor for the gas is less than 1. This means the gas is more compressible. For temperatures greater than the Boyle's temperature, the compressibility factor is greater than 1, hence it is less compressible. Ideal gas is not showing any compressibility. So mathematically we can say that Z is equal to P into V by RT, where P is the pressure, Vm is the molar volume of the gas, R is the gas constant, and T is the temperature. We can classify real gases in terms of compressibility also. By the formula, Z is equal to PVm by RT. Real gases can be classified into 3 types on the magnitude of the compressibility factor. For an ideal gas, the equation of state is given by PVm equal to RT, so that Z is equal to 1 at all temperatures and pressure. For PVm by RT greater than RT, we have Z is greater than 1. The gases having compressibility greater than 1 have a positive deviation from the ideal gases at all temperatures and pressures. Hydrogen and noble gases except krypton are examples. They have a low A value. For PVm less than RT, we have Z is less than 1. The gases having compressibility lesser than 1 show negative deviation from the ideal gases at all temperatures and pressure. Examples being the methane gas and the carbon dioxide gas. Such gases have large A values. Most of the gases show compressibility factor less than 1 at low pressures and greater than 1 at high pressures. So you can see from the curve, we have plotted Z versus P. And we have shown the variation of Z versus P at different temperatures. We can see that as temperature is increasing, Z is decreasing. The compressibility factor is inversely proportional to temperature. So, increase in temperature decreases the deviation from ideal behavior at certain temperatures. Every real gas has a certain temperature where the compressibility factor shows little changes and comes close to 1. Some gases obey ideal gas laws at high pressures at certain temperature. The temperature at which a real gas behaves like an ideal gas over a long range of pressure is the Boyle's temperature for the gas. For example, nitrogen has a Boyle's temperature of 323 Kelvin. Now let us move on to a very important calculation in real gases, which is the calculation of the critical constants for a van der Waals gas. By the critical constants we mean the calculation of critical temperature represented by Tc, the calculation of the critical volume represented by Vc, the calculation of the critical pressure represented by Pc, and the calculation of the critical coefficient represented by Rtc by PCVC. To calculate these critical coefficients constants, we should remember that at the critical point dP by dV has to be 0. At the point of inflection, d2b by dV2 is also equal to 0. Using these two formulas and applying it to the equation of state for a van der Waals gas, it is very easy to calculate Tc, Pc and Vc. So according to van der Waals equation, P plus A by V square into V minus B is equal to RT. Rearranging the terms, we get P is equal to RT over V minus B minus A by V square. Differentiating equation 1 with respect to volume, we get minus RT over V minus B whole square plus 2A by V cube. Doubly differentiating with respect to volume, we get d2P by dV2 is equal to 2RT over V minus B whole cube minus 6A by V4. At the critical point, that is T equal to Tc, P equal to Pc, V equal to Vc, we should have dP by dV equal to 0 and d2P by dV2 also equal to 0. Substituting these values into 3, we have Pc equal to Rtc over Vc minus B minus A by Vc square. Simplifying this further, we get Rtc over Vc minus B whole square is equal to 2A by Vc cube. If we simplify this more, we get Vc minus B by 2 is equal to Vc by 3, or 3Vc minus 3B is equal to 2Vc, or Vc is equal to 3B. So van der Waals equation of state predicts that the critical volume of the real gases should be 3 into B. It means it should be a constant, but this is in contrast to the observed results. Substituting Vc in 5, we get Rtc over 3b minus b whole square is equal to 2a over 3b cube. If we solve this further, we get Tc is equal to 8a by 27 br. Substituting Vc and Tc in fourth, we get Pc equal to 8ar over 27 br into 3b minus b minus a by 3b whole square. Simplifying this further, we get Pc is equal to a by 27 b square. Tc is 8a by 27 br. From these three formulas of Vc, Tc and Pc, let us now calculate what is a by b. We get a by b as 27 by 8 r into Tc, but Pc is a by 27 b square. So what we now get is, we get a by b square is equal to 27 Pc. Dividing them, we get b is equal to Rtc over 8 Pc. Substituting B in equation 10th, we will now get A is equal to 27 R square into Tc square over 64 Pc. The quantity RTC over PCVC is called critical coefficient, and RTC over PCVC is equal to 8 by 3 and should be the same for all gases as predicted by the van der Waals equation of state. But again, this is a prediction, and in observation this was not found to be true. So these are the calculations of the critical constants for a van der Waals gas. Next, let us calculate the reduced equation of state, or which is also called the law of corresponding states for a van der Waals gas. It is seen that the van der Waals equation of state contains A, B and R, the first two of which are the characteristic constants of a gas, and the third one is a universal gas constant. But what is seen is this, that because A and B are not a constant, they vary at different temperatures and are different for different gases. Hence, we can say that the equation of state, that is the van der Waals equation of state, is not a universal equation of state. So it needs certain modification to be applicable everywhere. The attempt of building up an equation of state which is of universal use succeeded in developing the reduced equation of state. If the three variables are measured in units of their corresponding critical values, then the resulting equation is called the reduced equation of states. Let us define the three reduced quantities as PR, VR, TR, and let us define them as PR is equal to P by PC, VR is equal to V by VC, TR is equal to T by TC, where PC, VC and TC are the critical constants, and PR, VR, TR are the reduced quantities. If we substitute these values into the van der Waals equation, we can easily find out that PR plus 3 by VR square into VR minus 1 by 3 is equal to 8 by 3 TR. Now, as you can see, that this equation does not contain any constants A and B, and this is called the reduced equation of state. This table is showing values of PR, VR, PC, VC, TC, Z, A and B for various real gases as determined by different equation of states. We have the van der Waals equation, we have the Berthelot real gas, we have the de Trisi real gases, and all of them are showing different values of PC, VC, TC, A and B. Depending upon which gas we are considering, we get different values of these particular constants. So this is as far as the real gases on the basis of van der Waals equation of state is concerned. In this class, this particular lecture, we have understood how to derive the van der Waals equation of state, how to find out the critical constants, how to find out the reduced equation of state, what is the role of the compressibility factor, how does it determine which gas can be compressed, which gas cannot be compressed. We have also seen the reduced equation of state, which is very important. It doesn't have any constants in it, so hence is universally applicable. We have also derived the Boyle's temperature. We have seen how Boyle's temperature is related to the critical temperature. So this lecture series, I hope, has given you some valuable insights into the working, into the physics, into the significance of real gases. And in my next lecture series, I will start with something different on real gases. So I hope you have understood, students, and meet you next time. Thanks.